Is it recording?
Yeah. So, hello everyone. Welcome to the 14th talk of the Higher Categories Reading Seminar. Today's speaker is Vaibhav and he'll be talking about mapping spaces as fibers and final objects, which is part of the fourth chapter of Cisinski. And you can see the references on the screen. So, yeah, Vaibhav, please take it away.
Yeah. The references is that Cisinski. This is Cisinski 4.2 and 4.3, and then higher turbulence theory a little bit, and Charles Rest notes, intro to quasi categories, where there's, I don't know if I think it's the same notes or it's very similar, but there's one called stuff on quasi categories, which I like the title of better. But anyway.
Wait, are you saying there are other notes titled stuff on quasi categories?
There's one called stuff on there's one called stuff on quasi categories, which I think is older. And then there's one, I think he taught a class and then made the notes a little nicer for the class, which became this one.
I see.
But
I see.
this is the one I read first, stuff on quasi categories. I just like how vague it is. It's just stuff, you know.
Yeah, sounds cool.
It's the same notes, more or less. Okay, so I might recall the join of simplicial sets, x and y. We had a simplicial set that was defined as star. He uses he will write this one, but I don't like that. But we defined a simple simplicial set that was the join of these two that is similar to the join of topological spaces. If you've ever seen that. And there's multiple ways of describing it. He describes it another way, but one way of thinking about it is as n simplices are simplices of like this: I plus j plus 1 equals n, and then you take I simplices of x and j simplices of y, right? And so in other words, n simplex in the join consists of and I simplex in x, a j simplex in y, and then this extra one that's appearing here is kind of like you're just connecting those two simplices by a delta one. So whatever this this is a cartoon. But this is kind of why it looks like, should remind us of the join of some topological spaces. Okay, and then there's phase degeneracy maps that are defined in a not in a way that sort of makes sense. But I don't want to go too into that because we should remember this from before. But this forms a functor. For any simplicial set x. Well, two functors actually. We have joining with x in one direction and joining with x in the other direction. And these are functors from simplicial sets to simplicial sets over x. Oh, sorry, under x. Right, because each join has a natural map of, there's an inclusion stuff y or y star x. Okay, and these guys have right adjoints. We'll call slicing. Now I'm just going to call both of them the same, but keep in mind that they're different slices. But so this first one, now we have join with x. I'm just going to call it slice, but we never actually use the name of this. But what you do basically is you take a thing like this and you form something we'll call over P. So it's a slice simplicial set over that map. And then the other one, I'll just write X. This one you write slice category under P. Okay, and well, let me just at least can write down what this guy looks like. You can describe it as in terms of this adjoint, basically. So S over P and simplices, simplicial maps, right, by definition. Simplicial maps into this guy. Which by this junction, same as simplicial maps over, under X from the join of this into X into S. And these are technically and what these mean, what I mean by this Homs and simplicial sets under X are, these are such that this commutes. Well, I guess I wrote that up, but okay. And this one is defined similarly, but it's underneath P. And note that any slice simplicial set comes projection. So basically you just take, if you have a simplex in this looks like this into S, right? And then you just take the n simplex and then you restrict it. And that forms an n simplex in S. Okay, we'll show that this thing is actually like a certain type of vibration. I think this one is a right vibration and the other one is a left vibration. Okay, and then, well, the point really is that this lets us describe a mapping space as a pullback. Or really as a maybe I should say mapping space in an infinity category. Okay, so let's describe it. Given an infinity category with objects X and Y. And define a simplicial set as a pullback. So you look at this over category. When I write C over an object, that just means C over the map, where this map is really zero simplex. You take this guy comes with its projection down to itself, and then x. And that forms this thing. And then similarly, go to the right mapping space, which looks similar, but instead of taking this over y, you take it under x. And then you take this y. Okay. So it turns out this is what he calls them in higher tables theory, but I think in Cisinski he calls them something different. Now I can't remember what he calls them, but this is what I'm used to. So in higher tables theory, he shows very early on that both of these guys are actually, I think he only shows this one or something, but they're very similar. So both of these are not just arbitrary simplicial sets, but they're actually concomplexes. So in some sense, this is why we want to call them like mapping spaces. Right? And then can show that actually let me say something else because you think of this guy as a space, you can think of this as a simplicial set as having, I don't know how to word this. So n simplices are described by you can kind of see it from this really. They are basically, they'll look like this is an n simplex, and then there's a y here. So this is really an n plus one simplex in C. So they have a bunch of it's an entirely degenerate n simplex. That's all x's, and then the other guy is y. So it's kind of like a cone-shaped thing. Similarly, this guy. Similarly, this guy will look like a bunch of degenerate simplex like this, and then an x on one side. So I remember in I took like category theory class with Ravenel a long time ago, like a few years ago, and he did a talk about infinity categories, and he defined these mapping spaces in this way. And so after that, every time I saw infinity categories, I was very confused because I kept seeing, or I kept thinking of, I was like, where is this definition of that when it came up? But yeah, so we can think of these mapping spaces in this way, and then it turns out that can show that these are equivalent. Obviously, we want them to be in some sense the same space. They should represent the space of maps between two objects in an infinity category. Can show that these are equivalent to each other in some sense. And both equivalent to the the usual mapping space. I would say usual, but guy we described earlier, I think in Cisinski, he calls it, doesn't call it this, but I want to call it this. I think it's Cisinski, he'll just call it C, that's why. This guy was just described it this way. Oops. This pull back. Okay, so it takes 4 chapters in this to show this. And Cisinski, it's in this chapter. But this is kind of the goal of this chapter, or this section 4.2, is showing that these are equivalent to this thing that we described earlier. And it turns out that in order to prove this, it's useful to describe an alternate construction. Write down what this looks like. So your equivalences look like, you can see this in Aristotle's theory. Right, and in order to show this, an alternate slice join construction. Okay, I'm not going to go super into detail because it's a little annoying and it doesn't really show up anywhere else besides showing us. She shall describe an alternate slice join construction, which are describe alternate slice join constructions, which are in some sense equivalent to the ordinary ones. And another place to look at this for these constructions and all these proofs are the risk. Okay, so I won't go super into detail, but at least I will talk about what these constructions look like. So, given simplicial sets x and y, the alternate join is a simplicial set described as the push out. Like this. Okay. And then similarly as before, can show this spectorial in both variables and the adjoints, which we'll call alternate slices. space. So this will take go to something that we'll call S over P, or Cisinski, he'll write S / P. This is what he calls it in rest, which I kind of like better, but it doesn't really matter. This guy's under. What is he called? P / S. Okay, so we're in infinity category X, and map of simplicial sets. There's an equivalence. Sorry, skipping out. There's a weak categorical equivalence. And remember, this is just weak equivalence in Joyal's model structure. It was like if you take geometric realizations of all their of all the mapping spaces and the weak equivalent as spaces. So there's a weak categorical equivalence between this join and the old join. And there's a map he describes called gamma. Okay, I'm not going to go into the proof or anything of that, but the proposition, and the next proposition is for an infinity category in a map of simplicial sets, there's an equivalence of infinity categories. I guess one thing we must have showed this at some point, but if you have if X is an infinity category here, no, if S is an infinity category here, then this over simplicial set is also an infinity category. Similar with this one, you slice simplicial sets. So there's given this T, there's an equivalence of infinity categories between the slices. Okay, so like I said, I'm just kind of rushing through this section, but this lets you describe a mapping space as a fiber of slice. Wait, okay. Yeah. We showed that. And as a fiber over the other guy, and then compare them. I'm just giving you sketches of what we do. You compare them, show that they're equivalent, and then you use them to show that both are. Both are equivalent to the usual mapping space. Okay. can see all this in Rust notes as well. Okay, so 4.1, we described a model structure on the over category for S we called the contravariant model structure. So I might write comma contravariant for that. And I didn't write down what all the vibrations and everything were, but weak equivalences anyway were let's see. Equivalences were I wrote it out in a special case, but you have X to S and Y to S. If you take X take these push outs, this is space X. Left or right cone is X joined with this guy, zero simplex. You take this, you take a push out of this form, and then you say you look at this induced map, and you ask that this is a weak categorical equivalence. Okay. You can see more of that in higher topos 3. And then there is also, let me see if I can find it. It's in 4.1. You can see all the vibrations and co-vibrations. There's 4.1.5. So co-vibrations are monomorphisms, and then vibrations are right vibrations. Let's write it down. Vibrations are right vibrations. Although you have to show this. Okay. And then the reason I brought this up is because we want to kind of find this set a notion of a final object, which generalizes final objects in ordinary category theory. But it'll look a little different at first. So an object is a final object if map I think we also defined, let me include this right here. A map, simplicial sets is called final. This was also from 4.1. Final if for any simplicial set T, the map. I might mess this up because I wrote this weirdly in my notes. We could go once and contravariant model structure. Okay, so we had this notion already. This was from 4.1 of a final map of simplicial sets, homomorphism of simplicial sets, and then we call an object a final object if the map is final in the sense book. In other words, this is why I was confused writing this, because I wrote this. So for any map, just sets X to S, D map delete the colons in this contravariant model structure. Okay, so one can show that X, an object X, a simplicial set is final and only if the induced map is a right and a Dom extension. I think this was all, this might have also been, or it should follow something in the earlier section as well. So let F be a map of simplicial sets. X a final object, X. Then F is final is consider it as an object, a final object in over Y. If and only if the object is a final object. Sorry, I think I can say F is maybe it's the same actually. F is final as a map. Simplicial set. If and only if this object is a final object in Y. Okay, and this proof is not too hard. I won't go into detail, but it follows from kind of closure properties. Let's see. 4.1.9 A and B. Basically, it comes down to like a 2 out of 3 property, and then yeah, like I think both of these are like 2s, some sort of 2 out of 3 properties. Okay, but I'm running out of time. So let X be a pointed simplicial set. Pointer simplicial set is just like, I guess we know what that means, or we know what that should mean, but it's just something of the distinguished point. Define a pointed simplicial set called C of X. X prime is this base point. You form and push out like this. Okay, so what does this even mean? So this guy is really, remind you of that. This guy is talked about, it's like a cone over X. The cartoon of this, you can draw as X. Then you, sorry, this I should mention what this map is. This map is base point join identity. So this thing goes to base point X. And then this thing goes to another thing, and then you join these two. Right, X join this is a cone over X, and then this is becoming a mess of the diagram. Okay. And then this collapses to a point. C of X will just look like this cone, but now your distinguished base point of it is this guy. Your distinguished base point is this cone point. So you're basically just forming a new object by forming a cone of your object that is going to be connected to every point in this thing, including your base point, and then you just consider that as your new base point. Okay. This forms functor. Pointed simplicial sets. So proposition is the new object, the new base point, the object prime is a final object in CX. Okay, so you're kind of just formally throwing in a final object because, and you can kind of see how it should. It looks like a final object because it's connected to everything by edges because of this join, and then it's your distinguished thing. Okay. I kind of got lost in the proof of this, so I'm not going to talk about it because there's other things I'm going to talk about, but I'm just going to say skipped because I literally only made these notes yesterday. But there's a lot more other stuff. Actually, I'm only halfway through my notes, so maybe I won't have time to even go through everything I wanted to go through. But functor C has a right adjoint. Does this? So it sends a pointed simplicial set to the over slice simplicial set, and then it gives it the base point, the identity. In other words, there's a projection. This technically X with the little base point, and this is the base point. And this guy also has base points. We'll let X be a simplicial set. Check little x. And then if there's a section, you consider the over category. You look at this projection down, and then you want to look at if there's a section like this, such that S of X equals X, then X is a final object. And if X is a infinity category, then this is an if only if. Maybe I can go through the proof of this. Do I want to go through the proof of this? No, a lot of stuff. Yeah, maybe I won't go through the proof of this because for time, but you can show that it comes down to some other closure properties. And then in the case of X being an infinity category, you want to construct such a section, and you can do that by some lifting problem over this guy. Anyway, I won't go through for that because it's not super interesting. I don't know why I started numbering them here, but let X be a simplicial set, an object. And you can show that the identity is in the final object in the category, which one would sort of expect. Well, this is like this one is a cool one version of the Nada. So let X be infinity category. Little X an object. Then the object and the contravariant model structure on this guy as vibrant replacement. Given by and remember vibrations are right vibrations. So this is what I was alluding to earlier, where I said we would show this guy was a right vibration, and this is kind of what that statement is. In particular, for all objects Y, there's an equivalence of infinity groupoids between these mapping spaces. I haven't defined what this one is, but I will. So map over X between over category over X and over category over Y. And the usual one maps over X. Okay, so this guy, this just define the pullback. This so you push forward by this. I'm just going to call it rho Y. Rho Y, and then this guy is let me take a look. This was something we saw earlier. So. And I think he has a different name for it, but I was getting confused because I think he called this also map X, and then he called this, yeah, I can't remember. Let me just, Cisinski, he called this map X over this guy to this guy. and then he calls this X. Just notational things, but this guy is the usual thing we described earlier. Okay, so there's an equivalence of infinity groupoids here, spaces, and so this is one of we saw that the identity is the final object in over category. This kind of sits like this. So by definition, this is final if and only if there's a weak equivalence. Really, a weak equivalence for any simplicial set, but in particular, there should be one of this form in the over simplicial sets over this. And then for any right vibrant for any right vibrant object, this is a row I the induced map here. Yeah. So this is something 4.1.14. Okay. Well, what is this guy? We read out that looks like by definition. That's just x over y. It's just x. And the y push forward is really just y. Yeah, and then so you can show that this guy over x is this pullback. Let's define this pullback. Which is space 5, 4.2. Which was something. This is how we define this as a fiber, right? Mapping space as a fiber. And so that shows that this is. Let's see. Almost out of time, but let me show you the other big theorem in this section. Which is a big if and only if. You can do to each other, so let X be a quasi-category, an object, and we'll call this denote the map. Okay. Then the following are equivalent. X is a final object. For any other object Y, the mapping space is contractible. The map pi is a trivial vibration. Pi is an equivalence infinity categories. Pi has a section sending X to the identity X. Any boundary inclusion fills to a simplex. Boundary with so this goes to in here. This will be U bar and such that U bar of n equals final object. Okay. Yeah, the proof of this is kind of long, so I'm not going to go into it. But maybe I'll just include it in the notes because I wrote it down. Yeah, and then can do some other things like show that final objects in an infinity category are the same, or a final object in an infinity category is a final object in the homotopic category, although the converse is not true. So let me write that down. corollary x in x final. What is x in homotopy categories final? But true. And other corollary that's kind of important is the final objects in an infinity category form and infinity groupoid. This is kind of the statement that well, form an infinity groupoid, which is either empty or contractible. So this is a statement that in ordinary category theory, that says that final objects are unique. Okay, and there's some other stuff, but I'm running out of time, so I will just call it there. Any comments or questions? All right. Yeah, so I guess just to recap, we showed that we can describe mapping spaces in an infinity category. We show that those things form spaces. We already saw that. We showed that these things are this guy, right? We showed this a long time ago. We showed that that was an infinity category. But then we had an alternate description as fibers over these over slice categories. And we showed that they're all equivalent in some suitable way, but we needed all this stuff to show that. And then we used that. This is the first kind of application of that, of extending the analogy from ordinary category theory to infinity category theory to final objects, which look strange at first, but then start to behave like you would expect them to behave, like final objects in ordinary categories. Right? Yeah, so I'm going to stop the recording now and figure out how.